same schedule. We'll do 50 minutes, and then
Okay.
try to do about 10 for discussion.
Okay, thank you very much. This is actually a little bit of an outlier for this conference. It's a little bit more of an operations research paper than, say, a political economy paper. It's joint work with Brian Roberson, who, as of the next fiscal year, will be at Purdue University. And this is part of a sort of long-term research project, and I'm going to talk a little bit about things related to that project in the introduction. But this picture shows you basically the type of problem that we're looking at. We're thinking of a game where two players, and we'll call one an attacker and one a defender, compete by allocating a continuous resource at a constant unit cost across different targets. And this picture going from left to right shows you a supra-network of networks that include several weakest link networks, in particular A, C, and E. And actually it will turn out, as you'll see almost immediately, that it really doesn't make any difference how we organize the weakest link networks in this system. And then what we call best shot networks, that the defender has to defend, basically keep intact the whole connection here. That is, the supra-network is a weakest link network composed of these sub-networks, some of which are best shot networks in the sense that in order to keep intact the connection B, the defender only has to succeed in the contest that takes place at one of these targets contained in the best shot network with 5 targets B. The same for the best shot network consisting of the 6 targets D. The defender only has to succeed in one of those in order to maintain that link. So this is the specific type of network that we're looking at. It's an overall weakest link supra-network from the standpoint of the defender, best shot from the standpoint of the attacker, but each sub-network may itself be either a weakest link or a best shot network. And so you can see almost immediately, for instance, that taking this type of approach allows us to think of things like theories of redundant systems, because if one can think of building in redundancies at a cost for some of these and turning some of these weakest link networks into best shot networks by adding components. Okay, so one can immediately sort of see that there may be some issues that one can address here having to do with overall systems. This is a specific example of a problem that involves multi-dimensional strategic resource allocation with linkages across the contests. So each of those targets is basically a contest. We're going to use a specific contest success function to define what the outcome of the contest is given the resource allocations. Usually if one thinks of a contest that involves a multi-dimensional allocation, we think of each particular target as being a battlefield, and the outcome is determined by the resources that are allocated to that battlefield. If you take an objective that's sort of a linear count, that you maximize the expected number of battlefields won, and you have separability of cost across the battlefields, then there's nothing that really holds the targets separately together. You can think of them each as a different contest. A number of us here have worked in that literature on single-dimensional contests. You can solve them separately. So a lot of the problems that are involved in things that we're looking at have to do with situations where there are linkages across contests. And obviously one very famous type of linkage coming on the cost side is through an overall budget constraint on your allocation of resources. And that's actually not what we're looking at here, but that's one particular type of linkage that one can have. And the perfect example of that is the classic Colonel Blotto game, where you have 2 players, A and B, and independent targets. Each player has a fixed amount of resources. These could vary across the players. We're going to use a specific contest success function in what we're looking at, which is the same as that employed by Borel. That is, the player that allocates a higher level of resources to a given target wins that target. So it's an auction contest success function. And in particular, we're going to look the Borel problem. Basically, you had equivalence between an objective of maximizing the expected number of wins across the individual targets and maximizing the probability of winning the majority because of the 3, in his case, 3 targets that he looked at. And in the original game, there's a 0 opportunity cost of resources. That is, your budget is use it or lose it, And if you don't use any of your resources, you don't gain anything from having held them back. And of course, in that type of context, generally there's no pure strategy equilibrium unless there's a very extreme asymmetry in the budgets. And a mixed strategy equilibrium, there is an n-variant distribution, one dimension for each of the n targets. And the support of the distributions have to be contained in the set of feasible allocations. So for instance, if the budgets are 1 and you have 3 battlefields, you can think of the set of feasible allocations as being the simplex in R3. If you look at that original Blotto game, there's been some activity in this area fairly recently. There's a lot of older activity. There are a couple of RAND memoranda by Gross and Wagner in the 50s. But more recently, there's been some interest in the problem. Indeed, my co-author, Brian Roberson, has solved the Blotto problem for asymmetric budgets, arbitrary asymmetric budgets. Dmitry Kvasov has a paper that in JET in 2007 that looks at the Blotto game and removes the use it or lose it feature. That is, he has a constant positive opportunity cost of resources up to the budget constraint. And in that paper, he looked at symmetric budgets. And Kvasov and Robertson have a paper that incorporate those two, the asymmetric budgets, together with the removal of the use it or lose it property. So there's a constant unit opportunity cost of the funds. And then there's some other contributions. Sergio Hart has a paper in International Journal of Game Theory in 2008 that looks at Blotto games with discrete resource allocation. And there's a paper in Public Choice by Goldman and Page that looks at a couple of other different objective functions and other types of assumptions on the contest success functions and the configuration of wins that one needs in order to win the overall, to win a positive payoff. If one looks at objective-based linkages, that is, instead of thinking of a budget constraint that holds together the contests and has some sort of linkage between the contests, but rather looks at an objective-based linkage. Obviously, one of the most prominent ones would be the assumption of a majority objective. That is, you win some prize if you win a majority of the battlefields, and of course we'd want the number of battlefields to be odd in this case. And if you don't win a majority, then you lose. And there's a very nice result that's, I actually have to admit that I looked at it for a very long time and worked on it for a very long time and could not figure out what the result is, but I contacted one of the authors, and there is indeed a very nice result that's embedded in the 2 Sanchez-Rosenthal papers in Games and Economic Behavior in 2003 that look at a game where you win a prize if you win 2 out of 3 battlefields, and you have a constant unit cost of expenditure, no budget constraints in that case. And and they also look at other, what I will call critical value count objectives. That is, they look at games where you win, if you win k out of n, where k is greater than the majority of the battlefields. And all of those that they look at tend to be symmetric objectives. That is, it's not obviously not a constant sum game because there's a positive opportunity cost of expenditure, but it could be the case that neither side wins because you're required to have a supermajority. What we look at in this particular paper is an asymmetric objective version. That is, we assume that one of the players has a weakest link objective and the other has a best shot objective. So that this particular paper fits into the realm of multi-dimensional strategic resource allocation with linkages. The linkages are objective-based in terms of the payoffs, and it's a particular asymmetric objective that we're looking at, and one that we can actually deal with. There are actually quite a large number of open problems, as I understand it in this literature. For instance, Sanchez and Rosenthal do not solve for this majority problem for an option. This is with auction success function with for n strictly greater than 3. As I understand it, that is an open problem. There are also some open problems with other contest success functions as well. What we're looking at, though, is again a situation where that contains as a special case one where the defender has a single weakest link network has to defend. The attacker wants to win, wins if he wins at least one particular target or battlefield. Okay, so again, weakest link network is one where the successful defense of the network requires the successful defense of all targets within the network. A best shot network is one where the successful defense of the network requires at least one target within the network be successfully defended. And as you saw in the configuration that I showed you earlier, we're actually looking at a super network that contains both weakest link and best shot subnetworks in this particular paper. The idea of looking at networks and targets in sort of a Blotto-like context, I believe, dates back to Schubach and Weber. They talked about the final status of the competitors is not determined merely by total individual targets, but depends on the relative value of capturing various configurations of targets. So they have certainly talked about this issue 30 years ago, but I don't really know of a whole lot of work that looks at this in the simultaneous move context. Now there is some related literature, and I'm going to divide this with some explanation into two basic streams of research. And within each of these there are quite a few differences, but one stream of research I'll call the contest literature, and what I distinguish as the contest literature is one which in some sense has a full strategy space for both of the players. So in the contest literature, not only does the defense get to expend some either continuous or non-trivial discrete resource, but the attacker does as well. So they in some sense have some symmetry with respect, maybe not complete symmetry, because you can talk about things like infrastructure, or I have another paper with Brian and Dan Ars on suicide bombers as sort of a lumpy type of technology, but there's some sort of symmetry in terms of the underlying strategy spaces that both sides have a non-trivial strategic allocation problem. Then there's what I would call the reliability literature, which is a combination of papers that either assume an exogenous probability of attack on different targets or derive that probability of attack endogenously. And this includes papers that appear in the engineering literature as well as the political science literature. In particular, for instance, the Powell papers have a defender. It has quite a rich structure for the defender that allows the defender to allocate resources and have nonlinear payoffs and so on across different targets. But the attacker generally is assumed to attack a single target and therefore chooses basically a set of probabilities with which it will attack single targets that sum to 1 across all of the targets. So I would call that generally the reliability literature, where usually in these cases the attacker's strategy space is in some sense a much simpler one than ones that appear in the contest literature, where both sides have quite often a non-trivial continuous allocation problem of resources. For instance, they have to allocate a budget of resources. And some of these deal with different contest success functions. The Clark and Conrad paper, as a matter of fact, deals with the same problem that we look at, but applies a lottery contest success function, where your probability of winning a given target is the ratio of your expenditure to the sum of the two expenditures of the players. Okay, so this is the model that we're looking at. Again, as I mentioned, that you have an attacker and a defender. You have n greater than or equal to 2 targets. You have k disjoint networks with nj targets in each network. We'll call the total number of targets again n. Let n sub j be the set of targets in network j, and we'll let the set of weakest link networks be script w, the set of best shot networks be script b. A best shot network, again, very simply, is one where, and basically here this is a specification of the tie-breaking rule, if the attacker has a higher resource allocation to at least higher resource allocation to every target in the network, this is best shot from the standpoint of the defender. If the attacker allocates a higher level of resource allocation to every target in the network, the attacker wins in that case. Otherwise, the defender wins. So we're giving ties to the defender in this case. That's what that's indicating. A weakest link network is one in which the attacker wins the network if there is at least one target for which it allocates a strictly higher level of resource than the defender. And again, we're going to treat the resource expenditure as one involving a constant unit cost of expenditure, so there's no budget constraint here. The linkages are coming on the side of the objective, and the attacker will win if it wins, since the overall super network is weakest link from the standpoint of the defender, the attacker will win if it wins one of the best shot networks or one of the weakest link networks. And in that case, it will have a payoff VA. That's a parameter of the model. And its cost will be the sum of its expenditures across the target. If the attacker doesn't win, the defender will win. He'll have a payoff VD. And again, he has his cost is the sum of the expenditures. Now, this treatment obviously can easily handle asymmetries in the cost, the per unit cost of expenditure, as long as that cost is constant in this context, because we can just divide through by that per unit cost and renormalize the value by dividing it through by the per unit cost C. So this type of formulation can handle differential efficiency of allocation as long as it's a constant returns type, and all that comes about simply by renormalizing the value of winning. So again, the strategies here are n-variate distributions, and we will parameterize the game by basically the network structure, which is given by the set of best shot subnetworks, the set of weakest link subnetworks, and then the value of winning for the attacker and winning for the defender, where again, if one wanted to talk about differential efficiency, all of that could be incorporated in the value. So that we saw that before. So this is the first theorem that we have. The first result is basically an example of an equilibrium. And in order to explain this, let me talk a little bit about this value alpha. It actually plays a prominent role in what we do. So because we're using an auction contest success function, this is sort of the sunk expenditure version of constant unit cost Bertrand competition. And generally what happens both in single dimensional contests with this type of success function and in multi-dimensional contests is that the competition is extremely cutthroat. A player who's in some sense disadvantaged, where that's appropriately defined, is going to get 0, is going to be driven down to his reservation value, and the other player will get some surplus, just as you would say in Bertrand competition, price competition, when you have different constant unit costs. So for instance, in a standard all-pay auction, if we had the same efficiency, and that is where you have a single contest with a constant unit cost of expenditure, and we had different valuations, the high value player would end up getting the difference between his value and the other player's value, and the low value player would get a 0 payoff. And something like that is happening here as well, except that one has to take into account the asymmetries that are generated by the network structure. So it's not just a matter of looking at the values, but you have to look at the values relative to what's needed in order to defend the values, to defend the network itself. And so alpha here is, in some sense, it's a ratio, it's a relative, you can think of that as a relative strength of the defender, where it's VD over VA, but in the denominator we're putting in this expression that has the number of targets in weakest link networks and the sum over all the best shot networks of 1 over the number of targets in each best shot network. So you can see right away that because the number of targets in weakest link networks enters in linearly as the sum there, that it really doesn't make any difference how I take these weakest link targets and combine them into weakest link networks. I have one big weakest link network that has all of those targets in it. I could call each target separately a weakest link network. But the best shot network, of course, because of the redundancy within a network, appears quite differently. So this term that has the targets within each network in it is a sort of a way of looking at the network structure and handicapping the defender based on the scope at which he has to defend all of these different subnetworks. So you can think of this as sort of the same type of term that one gets in an all-pay auction, the value of the defender over the value of the attacker, but it's normalized for the special needs that the defender has in order to defend the overall network. So the theorem says, this is an example of an equilibrium, and it depends on this relative strength of the defender. So there exists a Nash equilibrium of this game, and one such Nash equilibrium is the following. So if the defender is relatively, if alpha is greater than or equal to 1, that is the defender is relatively strong, the attacker is going to play a joint distribution that looks like this. So you can see in particular that it has a mass point at the vector of zeros. So the attacker in this case will, with positive probability, bid the vector of zeros, and that probability depends on alpha, depends on this relative strength of the defender. And then these terms basically, what you can see here is basically what's happening is in weakest link networks, the structure, the joint distribution is such that in weakest link networks, what the attacker is doing is basically pushing to the axes. He's putting all of his mass within weakest link networks to only one target, one particular target, and not spreading mass across several targets in the same allocation. He's randomizing which single target that will be, but the vectors that he's choosing will be vectors that only allocate a positive component to one of the targets in the weakest link networks. And the best shot network here, basically what he's doing is he's allocating equally within a given best shot network, he's allocating the same level of resource, but that level will be random. Okay, and that's what this min expression is picking up here. For the defender is basically allocating something that's basically along the diagonal. In the weakest link networks, he's always allocating the same amount to each of the components in a given weakest link network. And the best shot networks, he's basically plunging into one of the targets, because all he has to do is defend one target in the best shot network. So he'll always be in his best, well, in this particular equilibrium, he goes to, we'll show that later, but in this particular equilibrium, he'll plunge into one of the targets. That's better than spreading out the resources across a number of different ones. And again, because the defender is relatively, and this includes the case of symmetry when alpha is equal to 1, because the defender is relatively advantaged here, the attacker ends up getting an expected payoff of 0. That is, all the gains are being competed away, just as they would in a single dimensional contest. And the defender is getting an expression that basically depends on his strength. He's getting a payoff that depends on his relative strength. Okay, and then the second part of the same theorem is, again, just looking at the case where the attacker is stronger than the defender, and in this case, indeed, the defender is going to have a mass point at the vector of zeros. That is, he's going to not allocate anything to any target with positive probability, and pretty much the same type of pattern goes through otherwise, that the same type of logic that exists. In this case, the defender will end up getting a payoff of 0. And the attacker will get a payoff that depends on the attacker's relative strength here. So again, this is in some sense cutthroat competition and sunk resources across multiple dimensions where you have the network structure playing a role in determining who the stronger player is, that in a sort of non-trivial way. Okay, I don't need to, the volume of a box in these n dimensions is fairly straightforward. I don't need to tell you too much about that, but let me go through a couple examples here just to show you, again, just the intuition behind what it is that I just said. So suppose we have a single weakest link network with 2 targets, and indeed let's suppose that the players are equally situated. That is, in some sense, they're symmetric vis-a-vis in their value of winning relative to the network structure. The attacker is basically going to put uniform distributions on these two lines. That is, it's going to randomly choose one of the two targets to attack and randomly choose, according to a uniform distribution, how much resource to expend in that attack. And that's reflected by the joint distribution here. That's exactly what that's generating. The VD here is again equal to 2 VA. So that's why the VAs appear on the axes there. And the defender in this particular equilibrium is randomizing on the diagonal. That is, the defender is going to randomize and allocate in allocating this a random level of resource, but the same level to both targets in this case. And that's the payoff in that particular instance. And let me look at another example, just a slightly more complicated. This is one where you have a best shot network with two targets, X and Y, and a weakest link network with one target. Remember, if alpha is not 0, so one of the players is going to end up putting a mass point at the origin. Again, this is taking the case where they're equally situated, which for this particular network, there are two weakest link networks, so I add two weakest link targets, so I add up those two, so that's 2 coming out of that. And then there's, one weakest link network with one target, that's 1 coming out of that. And one best shot network with 2 targets. Sorry about that. So you add the weakest link network target, that's 1, and then 1 over the number of best shot network targets, so that's 1/2. So you want VD, to get alpha equals 1, VD will be equal to VA times 3/2. And in this situation, so again, the best shot network with 2 targets, X and Y, the attacker, in this case, will either choose to attack that best shot network, in which case it will allocate an equal amount to both because of the best shot nature. So it's on this diagonal, X and Y are the best shot network. The weakest link network is this one, so it may plunge into the weakest link network. So the amount that it plunges in here is random, and the amount that it places right here is random as well. So that's the attacker's joint distribution. And the defender's joint distribution will be one that randomizes, basically, it puts an equal amount on, it randomizes between either a component on the weakest link target Z and one of the 2 best shot targets, so that would be, say, Y, and this line right here is again the weakest link target Z and one of the 2 best shot targets X. So it's either going to allocate to Z and X together in this ratio indicated here. So this is VA over 2 and this is VA, where it's going to allocate to Z and Y together. But again, only one of X and Y, because that's a best shot network for the defender. Okay, so that gives you an example of an equilibrium, but we can actually say what some of the properties are for any equilibrium. Before I do that, let me just mention that there are multiple equilibria, and in particular, the defender doesn't necessarily have to allocate things right on the diagonal in the case of weakest link networks. There are other correlation structures that can exist for that case. And so another example of an equilibrium is the joint distribution here. This is for case 1 of the theorem that we gave, where the defender is relatively advantaged and the attacker ends up having the mass point. So this is another equilibrium, but we can say that there are unique equilibrium expected profits, and we can say that there are unique sets of univariate marginal distributions in this case. And in some sense, the univariate marginal distribution is determined by the fact that it's basically the attacker. Well, in all of these networks, one of the players has to just win one target. So it's either the attacker in weakest link, or in the best shot network, the defender has to win one target. So what are some of the properties of equilibrium? that will hold across any equilibrium? Well, for any two for any target in a weakest link network, the sort of standard things that you see in contests exist. So for instance, the defender and the attacker will have the same lower bound. The defender and the attacker will have the same upper bound. Within weakest link networks, that has to be the same upper bound across all of the weakest link networks. And it's given by the minimum of the attacker's value and alpha times the attacker's value, which depends on is the defender and the relative normalized value of the defender. If you have a best shot network, the same type of thing happens. That is, the attacker and the defender will have a common lower bound. These are sort of standard arguments that if it wasn't the same lower bound, then one of the players would rather go down to 0 on that dimension because it doesn't help them at all, but then the other one would also be willing to do that. And in this case, in the case of the best shot networks, there's a network-specific upper bound, but that upper bound is going to depend on the number of targets in the best shot network. So it will generally vary across best shot networks, and it's related to the weakest link upper bound, the common weakest link upper bound, by this relationship right here. The weakest link upper bound divided by the number of targets in the best shot network. So if you think of the degenerate case of a best shot network with one target as being actually a weakest link network, then these end up being identical there. And again, standard things for each target I, the marginal distribution for each player over the target is continuous, except for possibly a mass point at 0. So over the, one can rule out gaps in the marginal distributions the same way that one does in sort of standard all-pay auction-based analysis. So the first proposition that we can state on general properties of equilibrium is that the attacker will allocate a strictly positive level of force to at most one network. So remember, the overall super network is weakest link. So this is a property that sort of holds that if the attacker is going to attack a weakest link network, it's going to plunge in to one of the sub-networks. Okay. Now, that's sort of obvious in this context, but again, if you go back and think about this literature, a lot of the what we call the reliability-based literature assumes that. So one of the interesting things about this is it got us thinking about conditions under which that assumption is a reasonable assumption. So for instance, if you think of terrorist activity, it may be reasonable to think that the marginal benefit for a terrorist for that first fantastic attack is quite large relative to the benefit of the second one, say. And so in that type of context, maybe it's okay to think about a player, the attacker, allocating a strictly positive level of force to one network. Now remember, this is with an auction contest success function. So generally that's not true, for instance, with a lottery contest success function. So this gives you some conditions on both the objective and the success function to get that type of result that's assumed in some of the other literature. And similarly, if player A allocates a strictly positive level of force to a weakest link network, then one target in that network receives a strictly positive level of force. So that hierarchy there maintains that particular property. And then in each, sort of the dual of that for the defender, because the best shot network for the defender is sort of symmetric vis-a-vis weakest link for the attacker. In each best shot network, player D allocates a strictly positive level of force to at most one target in the network. Okay, I'll skip over, these are the same things. Here's the basic intuition for what's going on here with those results. And this is sort of the overall intuition about that type of, what's happening, is that if the attacker, I've shown this as a point, but think of this as positive mass in the interior, not on the axes here. Suppose the attacker is attacking a weakest link network with two targets, and it's somewhere in the interior here. That is, it has mass where it's allocating positive amounts to both targets. Okay, the probability that it's going to win at a point like this is the probability it wins on the first dimension. This is the marginal of the defender on the first target, plus the marginal of the defender evaluated at the y allocation on the second target, minus the probability that the defender allocates mass that's strictly dominated by the point xy. So it's basically everything over here plus everything over here, and then you have to subtract out the intersection. Okay. Well, suppose the defender has some equilibrium strategy that has marginal distributions that are given here, PD1 of x on the first target and PD2 of y on the second target. And let's construct a joint distribution that just says that the probability that the defender sets a value that's dominated by the point xy is the minimum of these two things. Okay, so whatever its distribution was before that you think in equilibrium, let's construct this distribution that just makes this the minimum of these two marginal values, okay? If that's the case, it's clear that that minimizes this probability that the attacker wins the weakest link network, because it's setting this expression equal to the minimum of these two, and it's clear that it can't be any higher than the minimum of those two. So it's setting it exactly equal to the maximum value that it can take. What that's doing is it's increasing the chance that the defender is going to win while not increasing his expenditure, because he's maintaining xy, the same marginal distributions of xy, so his expected expenditure is remaining the same. Okay, so basically by doing this, the defender is minimizing the probability that the attacker is going to win, which is maximizing the probability the defender is going to win. But if this is that distribution, then the attacker, if it's expending some value in that neighborhood, would do better by pushing it out to one of the axes. Because if the defender is playing this joint distribution that's the minimum of these two things, the attacker just wants to maximize the probability that's beating the minimum, beating one of those. And so the attacker is going to push all mass out to the axes in that case. And that's the underlying intuition for why you get that type of result. Okay, what are some of the other properties of equilibrium? So again, let's assume that the defender is relatively advantaged or equal in this case. So again, we're looking at the case where that measure of strength for the defender is greater than or equal to 1. Then we can say that each weakest link network is attacked with this probability, network J. So that's, of course, linear in the number of targets in the network, so how I decompose weakest link networks doesn't make any difference. Each best shot network is attacked with this probability, so the larger the numbers of targets in a best shot network, the less likely it is to be attacked. And the attacker will optimally launch no attack with this probability right here, which again depends on the asymmetry. And the larger is alpha, that is, the stronger the defender is in normalized terms given the network vis-a-vis the attacker, the less likely the attacker is to allocate positive probability anywhere. That is, the more likely it is to put a mass at 0, to opt out. And then if this is reversed, if alpha is less than 1, so the attacker is relatively advantaged, then basically the attacker is going to attack some target, that is, all of it will not abstain from attacking with positive probability. So the probabilities, if you add up the probabilities that attacks all the targets, they have to sum up to 1. And so the probability it attacks a weakest link network is this right here. The probability it attacks a best shot network is that. And then in this case, the defender will optimally leave the entire super network undefended with probability 1 minus alpha. So again, if the defender is very weak, it places a somewhat high probability on not defending in that case. Okay, how am I doing on time? When we start?
10 minutes.
10 minutes, okay. Well, let me talk about a few extensions, and then what I'll do, I won't go through any of the details. I have appendices and stuff on slides, but I will talk a little bit about some experiments that Roman Schur, Mehta, and I are doing. So what are the types of things that we're looking at in this context as extensions? Well, one of the things we started is looking at multiple types of investments, including things like discrete technologies that are somewhat destructive, but are not continuous. And we have a paper with Dan Ars on suicide operatives, viewing them as basically a very destructive technology that's lumpy in nature. And then also issues like public good or infrastructure technologies. So you can think of, instead of having to allocate resources to each battlefield independently, there could be some infrastructure technologies that if you allocate them, they apply to all of the battlefields. So that reduces the discriminatory ability for that particular allocation, but you, for instance, if it's more efficient. And actually that public good nature is the type of thing that you see in sort of the continuous Blotto versions that come out of the Lazzari-Persico public good paper in AER in 2001. One thing we haven't dealt with here is differential target values for the attacker and defender within the context of this type of weakest link or best shot structure. For the defender, it's not so much of an issue, but could have differential target values for the attacker. And then those of you who are familiar with the contest literature, one obvious extension is to think of something like affine handicapping within each target. So instead of allocating the target to the player that allocates the highest expenditure, there could be some networks that are naturally easier to defend or easier to attack, in which you can give one of the players a head start advantage in order in being able to capture that. And so that would be another type of extension. Let me talk a little bit about the experiments that Roman and Brian and I have been doing. So Roman and I actually have done some standard Blotto experiments with a co-author. And this particular experiment, we not only looked at the auction contest success function, but we also looked at the lottery contest success function within each battlefield, which again, the probability you win in that case is your expenditure over the sum of the two expenditures. So there's noise that appears in the outcome. And actually, the case of the lottery contest success function for this type of environment, the theoretical examination of that appeared in the paper in the Journal of Conflict Resolution by Kai Conrad and Derek Clark. Basically, in experiments, what we did is we looked at two types of situations. So we had 4 battlefields. We had a defender with a value, a VD of 200, and we looked at 2 different cases of the attacker, a strong attacker and a weak attacker. So we looked at attacker equal 40 and attacker value equal to 80. And this gives you a little bit of the data that we had. So we ran this both with the lottery and auction contest success functions, and we looked at both the case where the attacker is relatively weak and the attacker is relatively strong. And this gives you some of the predictions. Let's see. These are the predictions, or are these the? These are the predictions. So the probability of winning, the overall network here, the expected payoff that the players get in the 2 cases. So you can see again, actually in the lottery case, there's sort of strong asymmetry is distinguished from not too asymmetric. You can see in the auction contest success functions, again, one of the players has a 0 payoff in this. In this case, where the defender is strong, the attacker has a 0 payoff. When the attacker is strong, the defender has a 0 payoff. And these are the average allocations that you tend to see in the equilibrium.
So if the lottery, the attacker, they have 0, so that's the difference.
Yeah, so this is something that comes from the multiple battlefields. So if there's a strong asymmetry, basically what ends up happening is the attacker ends up randomizing with a 0 allocation and then some positive level. So it's not like what you see in a standard contest where there's a positive level. So you have sort of a trigger value of asymmetry that depends on the number, I think it's VA equals n minus 1. That depends on the number of battlefields. And if the attacker is relatively weak, it will end up playing this positive amount with positive probability in 0. The same thing happens with Lazier-Rosen contest success functions, things like that. So it's basically, it randomizes in a way to keep the other guy indifferent in that case. And so that happens in that very asymmetric case. But you're right, I mean, the standard one where things aren't too asymmetric is like what you would expect, that they're going to have a positive amount, a positive allocation. And here are the actual values that we generate in terms of average allocations and expected, and the payoffs and the actual probability of winning. So and eyeballing that, you can say it doesn't appear to be too far off qualitatively in terms of what happens, but there are some anomalies. As one sees in single dimension contests, what happens is, in this particular contest, is that there's over dissipation relative to the equilibrium. That is, people are too aggressive on average. Now, Roman and I have also run experiments on the Blotto games, and the nice thing about Blotto games is that it's a constant sum game. So there's no such thing as over dissipation because you can spend a fixed amount. As a matter of fact, the computer doesn't let you proceed until you've spent that fixed amount. The interesting thing that happens in standard Blotto games is that even though you can't be overly aggressive, you get the same type of behavior within each box that you tend to get in single dimensional contests as well as these contests. That is, you get more of a dichotomous choice, that within a box in the Blotto games, players either go low or decide to go for it and go high. And there's over dissipation because in the standard contest because they go high too much on average. Well, in the Blotto games, within a box they sort of do that, but in the aggregate they can't go high too much on average because they have a fixed expenditure. Here, because we have a constant unit cost of expenditure, so it's not constant sum, it's non-zero sum, non-constant sum, people end up being too aggressive. They spend too much relative to what they should, which is consistent with single contests. Now these are the empirical marginal distributions and the theoretical marginal distributions that you see, and it's actually quite interesting. So the lower set of panels here are for the 4 target case of the game we look at, that is the auction contest success function. And the straight line is what the equilibrium, or the solid line is what the equilibrium predicts. And so this is for the attacker and defender when the defender is stronger here, the attacker and defender when the attacker is stronger. And the upper level here is for the case of the lottery. And the interesting thing that we found here is actually doesn't look like the theory does too badly in the case of the auction, in the auction case. In particular, for instance, it seems to be the case that the attacker is allocating mass points. It's plunging in the way that it should. The interesting thing that comes out of this is that even for the lottery case, when the attacker seems to be, both when the attacker is strong and when it's not strong. So again, the solid lines are the equilibrium prediction. So for instance, here, their positive levels are chosen with probability 1, a fixed level here and a fixed level for the attacker. In this case, you can see that the attacker tends to allocate 0. It doesn't seem to take advantage of the fact of that sort of infinite marginal benefit at the margin, and it allocates 0 with positive probability to some of these battlefields. So even with the lottery contest success function, the experimental results sort of look a little bit like what you'd see with an auction contest success function, where the attacker seems to be plunging into a subset of the battlefields rather than spreading out and taking advantage of the positive terms that it gets in terms of the randomness for small allocations. So that's that for both the lottery and the auction contest success function. So overall, in terms of the experiments, as is the theory says, the attacker should play a guerrilla warfare strategy. And indeed, it looks like he does that. He stochastically allocates 0 resources to all but one target. That's about 81 to 89% of the time. Under the lottery contest success function, when the attacker is supposed to allocate a positive amount to every target, it actually doesn't do that often. 28% of the time he does that. 45% of the time, actually 45% of the time, the attacker leaves 3 targets untouched. So 1 minute. And then finally, in both the lottery and auction CSFs here, for the weakest link case that we're looking at, the defender looks like he uses what we call a complete coverage strategy. That is, the defender ends up allocating a strictly positive level of force to each target, as the theory would predict in that case. Okay, I'll stop right there then.
Two things. I was thinking first off that you were talking about how they tend to allocate all to one, the factor.
They tend, or the theory, you're talking about the theory or the experiments? They do it, yeah.
Both in the auction and the kernel
Yeah.
model. And so it seems to me that, just to run this up the flagpole, okay, it seems to me.
Well, wait, and the Blotto is something different. So the Blotto depends on asymmetries and so on. In a Blotto game, in a regular Blotto game with budget constraints, if you're the low budget guy, you would stochastically neglect battlefields. If you're the high budget guy, you don't.
But you're saying that they overdo they don't distribute things uniformly across the battlefield. They tend to do it all or nothing in both the.
Yes, that's correct. They're dichotomous within each battlefield.
And I'm thinking that maybe there's two different explanations. I mean, when I've run auctions in class, say an auction of incomplete information, they bid way too high. And
Are you talking about winner pay auctions or all pay auctions?
I'm talking about winner pay auctions.
Okay, because I've done work, I did some work with Charles Nussera on winner pay auctions with incomplete information. And the nature of the dissipation in winner pay auctions is very different from all pay auctions. In winner pay auctions, for instance, with incomplete information, say a uniform 0-100 distribution, the overbidding tends to be fairly uniform. That seems to be the prediction. I mean, if you look at the theoretical prediction, whatever your value is that you draw, say between 0 and 100, you tend to bid too much there. In all pay auctions is where you get the dichotomy, and at least that's what we found in those incomplete information cases. It's also true, for instance, in the Uri Gnesi's paper and some of the other papers that exist, is that the nature of dissipation doesn't come uniformly necessarily, but it comes from the fact that you're deciding sort of to go for it or not go for it.
So here's my point, that I'm thinking that the reason they overbid, at least in winner pay auctions, and sometimes they do it sounds like also in all pay auctions, is that they attach a great value to winning. At least if they're going to play, they want to win. They don't care how much they win, they just want to win.
Yeah.
But in Blotto, it's something else. They have a superstitious feeling that they can guess which battlefield it's going to attack. And so that's one thing I want to raise. The other thing I wanted to raise was when you draw out your data.
I have a different theory, but I'll tell you that later.
You're drawing CDFs.
Yeah.
And
those are marginal distributions. Yeah,
okay.
One-dimensional marginal distributions in box. I haven't drawn any joints.
Right. And I support drawing PDFs rather than CDFs, because when you draw a CDF, then there's already a given there. It's got to be increasing. And so to see what the discrepancy is, I have to kind of filter back to I have to start subtracting all along the line. And I'd like to see PDFs of all those experiments rather than CDFs. There's
one-dimensional PDFs or joint distributions.
No, I don't mind the joint, or I don't mean making one-dimensional rather than joint. I just want a PDF rather
of
than
anything, of whatever it is.
Then I don't. Then
okay, that's fine.
There's givens in the diagram. I know it's going to increase. I want to see the
Yeah.
discrepancy.
Okay.
I want to hear
That's
that
well. This does allow us to take care of the mass point, but that's that the PDF wouldn't, but necessarily. But
okay,
oh yeah.
those
So
are my two-
yeah.
are my two
Okay,
points.
that's good. Okay. Yeah. It's, I guess we could do something. We haven't done much with the joint. Visually, I was going to say.
4-dimensional CDS.
Yeah.
So what's your theory about why they go for all or nothing?
I think people I think there's a tendency, I think this occurs in a lot of different areas of this type of dichotomous choice. I mean, you see it in the marketing literature with consideration sets for products and things like that. I think it's a way of sort of boundedly, rationally reducing your decision in some sense, that you make a decision where you're sort of going to focus and go for things and where not. Now my overall theory is, and maybe we can test this on this, is that there's a type of territoriality that you feel, and this is something that's ingrained in our genes, that comes that you respect the territoriality, so you sort of stake out a certain set of territories that you think of as boxes that you're going to defend or something like that, and that you on average you're placing more to those boxes and neglecting the others. Now, that's one theory.
That's interesting.
That,
Any other questions?
We'd have to look at the dynamic structure for that, but there is a lot of serial correlation in these things. So I mean, that could be it. That's your stakeout territory, and you think of defending territory and possessing it the same way that you think of endowment effects or anything like this. And maybe it's genetic, maybe it comes from the days when we were hunter-gatherers or something. And yeah.
A couple things. One of the really nice features of your paper that was related to, but slightly different than what Bob Traeger did, is that rather than simply presenting the model and teasing out its implications, you also, in this case, did experimental stuff as opposed to sort of case study stuff to see whether it made sense. And I wanted just to actually mention what appears to be a fairly direct example in the real world, in recent American politics, of a situation that apparently mirrors the model, and that is the 2000 Electoral College contest. What we see when we look at electoral college contests is essentially an evolving game. That is, you can think of the game as involving initially some 50 states. Most of them are out of play. As the game continues, increasing numbers of them become effectively out of play. And they're recognized broadly that they're just gone, that it's not worth additional investments. And so by the time you're down toward the end of the electoral college contest, you're down to maybe 9, 10, 11 states. By the time you're down to the last few weeks of the contest, you're down to 3 states. Now my memory, I have a very descriptive paper about this and I can't remember all the details, is that by the time in 2000 you were down to the very end, you essentially had a best versus worst option situation, because you had a situation in which one of the 2 presidential candidates essentially had to win 3 states in order to win, and the other only had to win 1 of those states in order to win. And I would be very interested. I mean, now that we have this model, to see whether or not the sort of implications of that model in terms of where investments would go. Now, admittedly, it's complicated because a lot of investments in these things are done way in advance.
Well, it's complicated because the contest success function here is different, and we don't know exactly. I mean,
no, but it is right.
But,
it is.
But if it's close to the end, then it may be fairly deterministic. It's not completely. You don't need it to be completely deterministic.
Right.
It's
and it's more like an auction function. It's much more like really an auction function.
Yeah. So I mean, I have to. There is it Steinberg that has the paper, Stromberg that has the paper in AER. His paper, there's a little theoretical. The theoretical result isn't quite right, I don't think, in that paper, because it doesn't take into account the possibility of very small amounts of noise. The theorem is written generally for large amounts of noise, and for small amounts, you can show that these types of considerations that occur here arise in that type of context as well. So, I mean, one of the things about this particular success function is it does assume this extreme, but we know, for instance, from one-dimensional contests that if you, for instance, you have Tullock contest success functions with exponent greater than 2, we know that the payoffs are the same as there is an equilibrium where the payoffs are the same as the all-pay auction payoffs. We don't know what the complete set of equilibria look like for those games. But we do know that you don't sort of get pure strategies out of this type of randomization. And for instance, in Stromberg, I suspect the same thing happens. That for small amounts of noise, sort of not enough to generate pure strategy, you're getting this type of mixing that you get here as well. And I would expect your conjecture to hold that you don't have to assume this extreme.
And just a purely informational question. You had mentioned the existence of sort of affine handicapping games. Because that, again, is closer to what we observe when we look, for example, at the Electoral College, because we know that there are some states which historically are simply going to be much easier for the Democrats to win, and others where it's virtually impossible for them to win. What's out there on
Well,
that?
so Kai Conrad has a paper, I think it was an ER 2002, I think is his paper maybe, that does affine handicapping for a single, for all-pay auction success function with a single contest. And Meyerowitz has a paper that was it Journal of Politics just this last year that does something very similar to what Kai had done. What?
Shane Gale has an AR.
No, that's
That is in. Well,
that's caps and or nonlinear things. So with affine handicapping, Kai has a paper that does that, and Meyerowitz, this recent paper that he had, I think it's in Journal of Politics, does something very similar. for these Blotto-like games, I don't know of anything that does affine handicapping. I mean, I think it's, you know, you can go through examples and derive things, but to sort of get the general functional forms and things, I think would be quite hard, sort of arbitrary. You know, maybe we can do special cases. I mean, there's nothing theoretically that would be particularly unusual about that, but just, you know, because you have more parameters in that case to follow, I think it'd be hard to provide an overall characterization in that case.
You can think of Classos and Brian's layer work.
No, that's a cap. That's not the
Well,
same as
that's a cap.
Yeah, it's not
but
the same. It's not like a Head Start advantage or something like that. So that's different also. Yeah, that's the multidimensional version of Che Gale.
Yeah.
Well, our time is up. I think as we applaud our presenter, we also should thank our organizers,
Yes.
Don, Michelle, and Sarah.